In this video, I will be presenting to you the FUBINI'S theorem, which states that if the function f of xy is continuous on a rectangular region R, which is defined by the cross product of the interval a to b and c to d, then the double integral f of x and y dA is equal to the iterated integrals, which is the integral of f of x and y dx. So integrating first with respect to x from a to b, and then integrating with respect to y from c to d. This is also equal when you reverse the order of integration. Instead of performing the integration with respect to x first, here we will perform the integration with respect to y first. So integrating this function with respect to y from c to d, and then integrating next with respect to x from a to b, will have the same result as this one. So reversing the order of integration will not affect the result, since our domain is a rectangular region. And since the domain is a rectangular region, therefore our limits of integrations are all constants here. And this is illustrated in the example that we have in the previous video. So at this point, allow me to present to you the properties of double integrals. Let C be a constant and the functions f and g be continuous functions on region R, on which the function f of x and y attains a minimum value small m and the maximum value capital M, and let A of R denote the area of the region. If all the indicated integrals exist, then the following properties are true. Number 1, the double integral of a constant times a function f of x, y dA over a region. This is equal to the constant times the double integral of f of x, y dA over a region, which means that since C is a constant, we can factor it out and place it before the double integrals. And the proof of this is very simple, similar to the proof of the properties of single integral, which we've learned from your previous calculus. So number 2, we have the double integral of the function f of x and y added to another function g of x and y dA over a region R is equal to the double integral of the function f of xy dA over a region plus the double integral of your g of x and y dA over the same region, which means that the double integral of the sum of two functions is equal to the sum of the double integrals for each addends. And the proof is also the same proof you had in your previous calculus, the properties of single integrals. Number 3, the double integral of the function f of x, y dA over a region R is greater than or equal to 0 if the function f of x, y is greater than 0 on a region R. Which means that if a function starting from the xy plane or above the xy plane on a certain region R on the xy plane, then its double integral over that region is also greater than 0 or equal to 0 if the function is just the xy plane. Number 4 states that the double integral of the function f of xy dA over a region is greater than the product of its minimum value of the function times the area of the region, and also it is less than to the maximum value of the function times the area of the region R. In other words, because double integrals are interpreted as volumes of the solid under the surface F and above the region R, then its volume is greater than the minimum value times the area of the region, but less than the product of the maximum value and the area of the region R. Number 5. The double integral of the function f of xy dA over a region is greater than or equal to the double integral of the function g of xy dA over a region R if the function f is greater than or equal to the g function here on the region R, which means that the double integral of the function f is greater than or equal to the double integral to the function g if your f is greater than g over the region R. Number 6 property, and it states that the double integral of the function f of xy dA over a region R is equal to the double integral of the function f of xy dA over a region R sub 1 plus the double integral of the function f of xy over a region R sub 2 dA, where the whole region R is the disjoint union of R sub 1 and R sub 2, which means that if you subdivide the whole region into subregions and the disjoint union of these subregions, which is equal to R, then the sum of the double integrals for each subregion is equal to the double integral for the whole region. So this is subdividing the whole region into subregions. And this is true when the function is a continuous function, and even if not so continuous, but as long as the function is reasonably a well-behaved function. So number 7 property here, the double integral of the function f of xy dA over a region, and if this integrand f can be factored into two functions, say g of x and h of y dA over a region which is a rectangular region A to B cross C to D, this is equal to the integral from A to B of our g of x dx times the integral from C to D of our h of y dy, which means that if you can factor your f to a product of two functions wherein the first function is in terms of x alone and the second function is in terms of y alone, then the double integral to this product is equal to the product of the individual integrals, wherein we take the integral of your g function in terms of x with respect to x times the integral of y function with respect to y from c to d. Then the result is just the same with the double integral of the product of two functions. Now, take note that it happens sometimes, but it will not happen all the time. That you can factor your f as a product of two functions, wherein the first function is in terms of x and the other function is in terms of y alone. So let's see the reasoning here. So what is our reasoning for this generalization? Now, our reasoning here is that if we can factor out our f as a product of two functions wherein the first function is in terms of x and the second function is in terms of y over a region a to b cross c to d, then this is equal to the integral, the iterated integrals from c to d of the integral from a to b of g of x h of y dx dy here. Now, looking at this inner integral, which is with respect to x, because this is integrating our function with respect to x, we treat h of y as a constant. So this is just a constant with respect to the x integral. And since this is a constant, we can factor it out using our first property. So factoring it out in front of the integral, we have the integral from c to d of h of y of the integral of a to b of g of x dx and then dy as the differential y component of our outer integral. Now, take note that if we perform this integral, because this is integration with respect to x and our function is in terms of x alone, then the result is a number. Because the function is in terms of x, and using the fundamental theorem of calculus, we just substitute the limits of integration to our function, which is in terms of x alone. So therefore, the result is not a function, but it is just a number. So this is just a number because we integrate with respect to x. And since this is just a number, this is just a constant when we integrate this one with respect to y. So if we perform our outer integral with respect to y, we treat this one as a constant. So we can factor this out in front of this outer integral. So we have the integral from a to b of our g of x dx times the integral from c to d of our h of y dy. Now remember that this is just equal to the double integral of our product function as g of x and h of y with respect to the rectangular region a to b cross c to d. And how do we know that the limits of integration with respect to x is from a to b? It is from a to b because x should be taken from our x interval, and our limits of y should be taken from the interval of y. So this is the reasoning behind this number 7 property. And this can be illustrated with an example here. So suppose we want to evaluate the double integral of sine x cosine y with respect to a region R, where our R is the cross product from 0 to pi to 0 to pi over 2. So solving this one first as a whole, so we have the double integral from 0 to pi over 2 of the integral from 0 to pi of our sine x cosine y dx dy. So our limits of integration for x is from 0 to pi because that is the interval of x's. And the limits of integration for our outer integral, which is with respect to y, is from 0 to pi over 2 because that is the interval for y's. So integrating this one with respect to x first is equal to the negative cosine x cosine y from 0 to pi dy. Why? Because we treat this cosine y as a constant. So the only variable here is our sine x. And the integral of sine x is negative cosine x. Then evaluating this one from 0 to pi, we have negative cosine pi cosine y minus the negative of cosine 0 cosine y there dy. So we have the integral from 0 to pi over 2. We know that cosine pi is negative 1. So this is negative 1 cosine y plus the cosine of 0, which is 1. And the negative of the negative is positive. So 1 cosine y dy. So what will you have is the integral from 0 to pi over 2 of cosine y plus cosine y. So we have here from 0 to pi over 2 of 2 cosine y dy. And the integral of cosine y is sine y. So we have 2 sine y evaluated from 0 to pi over 2. And this is equal to 2 sine of pi over 2 minus 2 sine 0. And sine of pi over 2 is 1. So times 2, that's 2. But sine of 0 is 0. And times 2 is 0. So 2 minus 0 is 2. So we will check it here whether this one is equal to the integral of sine x dx from 0 to pi times the integral of cosine of y dy from 0 to pi over 2. So we will check whether the result of this is the same as the result of this one, so that we can verify this claim here. So what is the integral of sine x with respect to x? That is negative cosine x, and this will be evaluated from 0 to pi. And this will be multiplied to the integral of cosine y. And the integral of cosine y with respect to y is sine y. And this will be evaluated from 0 to pi over 2. So, substituting our pi here, that is negative cosine of pi minus the negative of cosine of 0, which will be multiplied to the sine of pi over 2 minus sine of 0. And what is the cosine of pi? The cosine of pi is negative 1. And the negative of the negative is positive. But the cosine of 0 is 1. And this will be multiplied by the sine of pi over 2. And the sine of pi over 2 is 1, but the sine of 0 is 0. So this is actually 1 plus 1 here, and this will be multiplied by 1 minus 0, which is 1. And 1 plus 1 equals 2, and multiplied by 1 equals 2. And hence, we see that the two results are the same, which means that our claim here is verified, which is our 7th property in the integrals. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.